Hello again. This is ME4111, Engine Mechanics 1. We're working through tutorial sheet 5, and our questions are getting progressively more difficult. So we're currently on question 8. This is for all those wannabe aeronautical engineers out there. So we got some sort of an aircraft, twin engine. So they're testing it, and during that test, the engine is revved up, and a 2 kilonewton thrust is generated, which is indicated here. So the main wheels at B and C, so B is there and C is the far side of that, just under the engine, are braked in order to prevent motion. So our system is in equilibrium still. And we're asked to determine the change compared to the nominal values when the engines are off in the normal reaction forces at A, B, and C. So the normal reaction forces will be the forces pointing up. So we're after the change in those loading conditions at A, B, and C, just the vertical ones, which are the normal components. Now, so this one again needs a bit of thinking, but our first automatic step is to draw a free body diagram. So again, you don't need to do a beautiful picture of the airplane. I've just represented it as a series of lines. And I've indicated the forces acting. So at point B, I have my normal reaction force in column BZ because I have a Z direction indicated there in my coordinate system. I have my x-axis running down the center line of the fuselage. So AZ is acting out here. So point A. I've included the weight of this aircraft. We're not told what the weight is. We have no info on that. But the whole point of these reaction loads is that it carries the weight. So we have that there. So I've indicated that. I'll just put it a distance L for argument's sake, some distance along there. I don't know where it is. Maybe it's further down there. But I'm just saying it's there for the time being. And I'll put it bang on the center axis because if it's not bang on the center axis, it's going to be very, very hard to fly. So the aircraft will be designed to have it that way. I'm measuring for B and C. And then what I've shown in this kind of pinky color is the additional forces that arise when the test is performed. So we get this 2 kilonewton force acting here. And then due to the braking, we have CX and BX come into play. Now, essentially what I have there is 2 free body diagrams in one, but they're differentiated by the pink color. Okay, so the values of AZ between the loaded and unloading condition change. All right, so that's what the question is asking us to do. So we need to have a look at this and figure out what we're going to do. Now, the first thing is, if we think back to the previous example, what I did was I took moments about a point where a lot of forces were acting. So if I look at the y-axis here, I would have a number of forces acting that cause moments, and a lot of them they're knocked out. But I'd also, when this is kicked in, I would have an additional force, and that would change AZ. So if I take moments about the y-axis, I should be able to figure out what the change in AZ is. So that's my first method or target to go for. So I left my free body diagram in. I'm no longer looking at the picture. This now I'm what I'm basing my solution off. So I've chosen that y-axis, and so I'm taking moments about this axis along here. And the forces that contribute to it are this one here with that distance, W, and this one here, okay, with those distances. Okay, so they're the forces that cause a rotation about that axis. You see that this one causes a rotation like that. This one also causes a rotation like that, the weight, and then this one causes a rotation in the opposite direction. Okay, so I just cleared it up a bit. So that's what I've done here. And first of all, I've done it for the unloaded case. When there's no thrust, I have AZ times 4 minus W times L equals 0. So I get AZ is WL over 4 when there's no thrust present. Then the engine is kicked on, and now my situation changes, and I have this additional term kicks in. Okay, so AZ times 4 minus WL minus 2 times 2. So 2 for the kilonewtons magnitude and 2 for the distance. and minus for the direction of the rotation. Okay, so that gives me AZ is WL plus 4 over 4, which is WL over 4 plus 1. And if I compare that to what I have up here, previously it was WL over 4. So by throwing on the 2 kilonewton thrust, I've added 1 kilonewton onto AZ. So AZ has increased by 1 kilonewton. Okay, so that gives me that answer out. Right, so if I look down at the sum of my forces, everything in the Z direction is pointing up or down, right? So BZ, CZ, W, and AZ. So when there's no engine on, they support the weight of the aircraft. Then when this thrust kicks in, AZ changes, but there's no other forces acting in those directions. So I have BZ plus CZ plus AZ minus W equals 0, whether or not the engine is on. And what I've had is that AZ has increased. So W is going to be constant. That's the weight of the aircraft isn't going to change. Therefore, BZ and CZ are going to decrease, compensate for that. And they're going to decrease by 1,000. Okay, because AZ went up by 1,000, there's nothing else can change. So I know they're going to change by 1,000, decrease. Now I need to figure out, well, how are they going to decrease individually? How's that going to be distributed? So if I now look at my x-axis, so if I take this axis along here, and I take moments about that axis, it's a pretty straightforward balance. So I have BZ times 2.4, which is going in the clockwise direction around it, so it's minus, plus CZ times 2.4, which is going in anti-clockwise direction, so that's positive, equals 0. And none of the other forces are causing the rotation about that axis. So that gives me the simple result that BZ is equal to CZ. And again, that makes sense if you think in terms of the way an aircraft is designed. You know, we'd have the landing gear taking equal loads at B and C. So therefore, the fact I've increased AZ by 1,000 newtons from my sum of the forces equals 0, which doesn't change whether it's loaded or unloaded. We can see that if I've increased this by 1,000, as I said, these two have decreased by 1,000 and they're equal. So they decrease by 500 newtons each, which is the answer. Yep, so minus 500 each and 1,000 then for A. So 1 kilonewton up for AZ and half a kilonewton each at BZ and CZ. Okay, so that's quite an interesting problem because it gets you to think about how you're approaching things. And again, it looks quite complicated, but if you work your way through it, using your principles, you should be able to work out the answer. And it also kind of gives you, I think, a good understanding of the kind of changes that can happen. And just be careful in things that, you know, people tend to think that, okay, because this force is pointing this way, you know, I've changed the loading on the system, I've introduced this. So all these forces will not necessarily change. Well, they do, because and you see how it changes when we take moments about the y-axis. Okay, so that causes the reaction component at A to change. Once that changes, then the loads in the other two change also. So just because you introduce this force coming in this x direction, you cannot assume that the vertical component, reaction components stay the same. So always be very, very conscious of that. When the loading condition changes, the reaction forces likely change. So don't assume that they are, assume that they change. Okay, there's quite a lot to digest in that. Just go back over it and see if you can work through it yourself and really just try and understand the logic. The key thing really is to get your free body diagram and then look at it and try and understand your plan of attack. Okay, and in this problem, you weren't given any information on the weight. So you need to factor that into it and look at the change in AZ, which I did here, relative to the weight of the aircraft also. Okay, so that makes it reasonably straightforward to work out. But it's easy when you've seen it done. It's more difficult to solve that from scratch. And really, that's the way I want you to get you doing things is that you draw a free body diagram, you look at the forces that are on it, and then you plan out how you're going to solve it. And you it's a very deliberate solution that you're going for, rather than one that you've written off or learned off by heart. Okay, any questions or comments, just come back to me, and we'll see you again soon. Bye-bye.